Hey, we're going to do support vector machines now. Woohoo! All right, so what's a support vector machine? It is like logistic regression in that we are looking at some kind of classifier that's going to generate predictions that are a function of x and w, right? So it's some sort of linear algebra thingy, just like logistic regression. There's several differences we're going to go into in great detail. Obviously, it's going to have a loss function, right? And so one of its key points of difference with logistic regression is what this loss function minimizes. Logistic regression goes after maximizing the probability of correct prediction for every data point. And that implicitly ends up being, well, not implicitly, explicitly, just some algebra, right? It ends up being minimizing what's called the log loss. That's logistic regression. Okay, so logistic regression minimizes log loss. In support vector machines, what we're going to try to do is maximize the margins. We're going to talk about what margins are, at the same time that we also minimize misclassification. Okay, so there's two terms to this loss function. This loss function is going to have a misclass term and a term that is going to ask us to maximize margins. Okay, let's get into what margins are then. If I was going to draw a decision boundary for these positive class and negative class dots here, it's pretty easy to draw many different decision boundaries. Which one would be the best? We could draw a decision boundary like this. We could draw a decision boundary like this. Both of those intuitively seem not great. Okay? We could draw a decision boundary like this. Also seems not great. Why do these seem not great? Because we kind of intuitively know that these particular data points, they're noisy, right? We could get a brand new data sample and it could be over here. Well, two of those three lines would be up the creek without the proverbial paddle at that point, right? We'd end up with an error. So, one way, given that kind of, statistical viewpoint, the idea that there is some true mean of x here and noisy measurements happen around that x, right? We want to put our decision boundaries such that we have the least chance of having a new noisy example go on the wrong side of the boundary. Okay, in order to do that, we might pick out what data point is closest to the negative class. Okay, and on the negative class, what data point is closest to the positive class? If these are our two closest data points, we might want to essentially put the decision boundary smack dab in the middle between them. Okay, so that's one of our intuitions here. We want to draw a decision boundary that lies smack in the middle, as good as my art is able to show you in the middle, between these two. So maybe something a little bit more like that, where what we're trying to do is make this smack in the middle so that those perpendicular distances are equal. And to give you the clue about what margins are the distance here so the margin is 2D. That's how big a space we got in the middle where noise can happen. All right, so this is our support vector machine idea. We want to place decision boundaries such that the gutter, this like free zone, no man's land, that we keep data points out of this gutter. That is the main idea. All right, let's do some math that we're going to need. So previously, we have mentioned the idea that the projection of vector A onto vector B is a dot product. Right? We've talked about this as A dot B as this projection. Wow, I cannot write today. Right? We've said something like that projection is A dot B. The thing is it's not really. Okay? Like A dot B is unnormalized. A dot B is in units of the size of vector B. So you can see that more clearly if we look at one of the definitions of dot product. A dot B is equal to the magnitude of vector A, the magnitude of vector B, all of that multiplied by the cosine of the angle in between them. Okay? The thing is if you do a little math, you realize that if we know that this side over here, right, this distance, that's the magnitude of A cosine theta. Okay, so if A dot B is A cosine theta, what happens to that B? That B has got to move over here. So that's how we end up with this formulation. This is now in contrast to the idea that A dot B is the perpendicular distance. Just note that that A dot B is in units. So that's in units of magnitude on vector B. So whatever that thing is, it is the perpendicular distance. It's just that the units are not absolute. Whereas this is in units of centimeters or inches or whatever you want. It's in absolute units. Okay? So this kind of normalized distance is telling us how to measure that size of that margin. Okay, so we can turn A and B into the more familiar things we're actually working with here. A data point X and the weight vector for the decision boundary. So if we want to know the total distance, the projection of X onto W in absolute distance, it's going to be W dot X divided by the size of W. Okay, so we know W transpose X over W is the distance between the hyperplane of the decision boundary and a given data point. We want to make those margins big, so we need to pick those data points that are closest together, and we want to draw a line in between them where we have maximized this D. Okay? So it works like this. We don't just need the two closest data points the way I alluded to earlier. We actually need 3 for this particular dimensionality of data. Why do we need 3? Because we have lines. Decision boundaries are lines when we're in 2D. They're planes in 3D. But to determine a line, we need 2 points. That's how we know the slope of the decision boundary. So we've got to pick 2 points that are closest to the other side. And those 2 points are going to determine the slope of our decision boundary. We also need a third point, but we only need 1 point over here because we already determined the slope here, right? And this point over here is going to be the one closest to these 2 over there. So we're going to draw 2 lines, same slope in both cases. We're going to call this one the positive hyperplane. And this one is the negative hyperplane. These define the gutter. They define the no man's land where data points should not lie. Now, we have done something fairly arbitrary. We have said that WTX is equal to +1 defines this place, and WTX equal to -1 defines this place. What we've said is that these things are one unit of weight vector away from the decision boundary. So the decision boundary lies right in the middle, smack dab in the middle between them, and it lies one unit of weight vector size away. Or more to the point, 1 over, I need to be very precise here. It lies 1 over the weight vector magnitude away. So not a weight vector magnitude away, 1 over the weight vector magnitude away. And the margin, the size of the margin we're trying to maximize is 2 times those d's. Okay, so d is equal to 1 over the margin, and the margin is therefore 2 over the magnitude of the weight vector. So this is the thing we're trying to make big as possible. Right? We want to pick the weight vector that plops us down such that we have the best possible margin. That is our goal. Okay, just a note that we can, of course, note that the weight vector, the L2 norm of the weight vector is the same thing as the square root of W transpose W. The L2 norm is, the square root of the sum of squares. This bit in here is the sum of squares, so if we take its square root, that is the L2 norm. Okay. So, knowing that we have this inverse relationship to margin size, what we can say is that when we have a giant weight vector, then the size of our margins is going to be very, very small. And when we have a tiny weight vector, the size of our margins is going to be very, very big because of that inverse relationship. So what we're looking for effectively by maximizing the margin is we are trying to minimize the magnitude of the weight vector. Oops, okay. So training a support vector machine, what we're going to do is we're going to have 2 terms, right? We're going to minimize the weight vector, which is going to maximize our margin and make it less likely that we have any problems with misclassification. We also are going to have a separate term that's going to explicitly minimize misclassification in a very particular way. This is called the hinge loss. So there's 2 terms to our loss function. Okay, so here's the hinge loss. The idea of the hinge loss is that we don't want any data points living in this margin. We don't want any training data in there. We said that explicitly a minute ago. So how can we do that? We're going to not just penalize for being on the wrong side of the decision boundary. If I have a positive class instance over here, that's clearly bad. It's the wrong side. We're going to get a misclassification, right? But I also want to penalize if my positive class instance lies in here because I haven't kept my gutter clean. I've allowed it to get all cluttered up, and we want to penalize that. But this is not as bad as this. So that's the nature of the hinge loss here. If I have some data point in this place, well, I want to penalize that for being on the wrong side of the margin of the positive hyperplane. Where is the positive hyperplane located? By the construction of it, that's one weight vector, one over weight vector magnitude away from the decision boundary. It's +1 away. So if I am greater than +1 over weight vector magnitude away from the decision boundary, I'm good. There's no error over here. This is a good data point. If I'm just less than 1 over weight vector magnitude, then I should have a small penalty. Okay? So that's what we see here. That is less than 1, but it's still bigger than 0, which is where the decision boundary is. Okay, so it has just a little bit of loss. Now, if I have a negative class point here, that negative class point is completely on the wrong side of everything. And if it's completely on the wrong side of everything, that should be a big loss. So it is on the wrong side of the decision boundary, and therefore it gets a bigger loss. This is the so-called hinge loss. And the reason it's called a hinge is because it makes the shape of a door hinged to the door frame. That's the idea here. Okay, so this is the hinge loss. It's a term which is misclassification error plus a little bit of oomph if we're on the right side of the decision boundary, but the wrong side of the positive margin. Okay, that's it. Hope you all had fun. Talk to you soon.